Hi, everyone. Before I get started, I wanted to say what a pleasure it is to be participating in the UConn Sports Analytics Symposium. I know Junyan and his fellow organizers have made a tremendous effort to create a sports analytics event that's accessible to interested students. And I want to thank them and all of the staff who've made this event possible. For those of you that I haven't had an opportunity to meet, I wanted to say a little about my work. I'm currently a senior data scientist at Zelus Analytics, where we're building the world's best sports intelligence platforms. In my time working as a data scientist in sport, and particularly my work at Zelus, I found that latent variables, or the quantification of things not readily observed, is a recurring theme. So today I wanted to talk to you about a class of models that are great tools for a range of latent variable problems. These are mixture models. Although my work at Zelus, I'm lucky to get to work on multiple sports. Tennis is the sport I know best, and all of the examples in my talk will come from tennis. But if this talk does what I intend, you'll see that all the models I describe have direct relevance to problems in all of sport. So to dive in and make that last point more concrete, I wanted to first consider three different topics that are of major interest to performance assessment in tennis: quality of shot, playing style, and player injury. These are important areas for analysis in tennis, but they're topics that wouldn't seem to have that much else in common. But if we think about developing a model to get at any of these things, we would quickly find that they are all very common in one basic property, and that's that the central thing we want to model isn't something we can readily observe. There's no single physical measurement of a shot that captures its quality, just as there is no single outcome that tells us all we need to understand about a player's style. And although we might be able to observe some specific injuries, our window into the ups and downs of a player's fitness is very limited. So for all of the topics, the concept of primary interest is something that's fundamentally intangible. If we want to try to quantify these unobservables, we need a strategy to infer them from what can be observed. So in this talk, I want to show you that mixture models are a powerful set of tools for a variety of latent variable problems. And I'm going to do that by walking through three different latent variable problems in tennis. Now, why am I pushing mixture models so hard? Well, as I've already stressed, they are a general strategy for introducing unobservable quantities into a model and do it in an intuitive way. Intuitive because the observables can be thought of as unknown subgroup categories. And that's something easier for us to get our heads around than, say, a hidden layer in a neural net, which is also a latent thing, but far more abstract. The analogy of mixture components to unobserved subgroups directly relates to another take on mixture models, and that's as an approach for unobserved clustering. There are a lot of clustering methods out there, but a strength of mixture-based clustering is that they are probabilistic, and the use of clusters will be driven by likelihood-based principles. The last major reason to like mixtures that I'll mention here is that they can help to model variables with non-standard distributions. So if you face a problem that falls into any of these three categories, mixture models would be a good candidate to consider. Now, if you think a mixture model is only suitable for problems with clear structure, like when you see a distribution with multiple modes, I wanted to show that mixtures have much greater applicability than those cases would suggest. We can see this with this very simple single variable normal mixture. Each example that you see in this animation is a case of a three-component mixture where each observation comes from one of the three normal distributions having their own mean and variance. When we look at the combined distribution, the result of the three mixtures, we see in some cases clear three groups represented and different modes for each. But we can also see examples where the impact of the mixture is only in creating an asymmetrical shape or something that looks normal but maybe has heavier tails, for example. So they're all non-standard, but not necessarily multimodal. And this should just give you an idea of more general ways in which mixtures can occur. Okay, so now that I've hyped up the mixture model, let's actually get into technical details. The model structure I'm going to describe is what I think of as a Bayesian recipe for a mixture model. One, because it's fully Bayesian, and two, because I've done it in a general way by not specifying the exact distribution of the likelihood. So this will allow it to apply to many types of observations. I'm going to be using Bayesian inference throughout the talk, but I do want to stress that mixture models can be fit with frequentist-based approaches such as EM. However, in addition to the standard strengths of Bayesian inference, when it comes to mixture models, I found that software that's based on EM, for example, can be highly specialized, which can limit its range of use for the problems that we might want to apply it to, the kinds of problems that we'll come across as sports statisticians. So this is my reason for emphasizing Bayesian-based approaches. Okay, so the Bayesian recipe here is for a finite mixture model. The finite here refers to the fact that we have k mixture components, and we're going to assume that those are known. This assumption can be relaxed, and we can actually make the component k part of our model inference strategy. But for this talk, I'm just going to take this more basic approach just to get us some groundwork. Okay, the outcome of the model in this notation is denoted by the variable y, which has some dimension d, so it could be variant. Since it's usually easier to think about our data, let's start from the bottom of our recipe where the likelihood is specified. The key thing with the mixture model is that we think of the likelihood as conditional on the unobserved component k, one of the mixture components. We assume that every y comes from the same family distribution, whichever component it is, but that the parameters defining that distribution are specific to that mixture component. Now note again that I've not specified what that distribution actually is. This could be multivariate normal, or it could be a D-length set of probabilities defining a multinomial distribution. All of these are possibilities. Whichever case is the one that's appropriate for your specific problem, that will determine what the form of the likelihood will take, as well as what reasonable choices of hyperparameter distributions you'll have. For any of these cases, the mixture components will be generated by a simplex parameter that I've denoted here as lambda, and a natural choice of prior for those lambda probabilities is the Dirichlet distribution. So this is our general recipe. Let's make it a bit more concrete by considering a specific application. I mentioned previously that one of the areas of a lot of interest in tennis is defining player style. Style boils down to a player's shot preferences and the specific shot types that they use the most. As the serve is the most important shot in tennis, there's particular interest in understanding players' serving styles. Now, the more we can measure about the characteristics of any shot, the better we're able to distinguish among different types of styles that players use. Tracking data provides the most detailed information that we currently have available to us about shots, and it is regularly captured at professional matches through the use of the Hawkeye player challenge system. Sadly, most Hawkeye data is not publicly available, but starting in 2017, due to a partnership between Infosys and ATP Media, some Hawkeye data is actually on the web and can be scraped through the ATP's second screen feature. This includes aggregated information about a number of shot characteristics, including speeds and shot placement, for example. And the speed information is what I'm going to focus on in this example of player serve style. So in this slide, we can see the distribution of the average first serve and second serve speeds for ATP matches played from 2018 through 2020. All of the speed measurements are going to be in kph. And looking at these plots, we see that the average for first serve is around 190, while the average for second is around 160. We see in the first distribution that there's some left tail for some cases of matches with lower than typical first serve speeds. We also see from the scatter plot that there is a strong relationship between a player's first serve average and their second serve average in terms of speed. Also, the elliptical shape suggests that we could try to model this with a single bivariate normal, but there are a few reasons to suspect that a mixture could do better. The reason being that there are a number of causes we can imagine that would result in heterogeneous groups in terms of serving speed from one match to another. For example, some players may have biomechanics, perhaps due to their height, for example, that would allow them to hit some serves more often than others. Also, due to player preferences or strategy, these would also be things that could influence how they serve in any particular match, as well as their overall fitness level, their ability to execute the serves that they would like to. So any of these could be a reason to explore a mixture model for this serving data. Okay, so let's go back to our recipe and now actually apply it to the specific case. So with our serve data, we have a two-dimensional outcome, one for first serve speed and the other for second serve speed. Beginning with our likelihood, our exploratory plot suggested that a bivariate normal would be a reasonable choice for our observations. Okay, so that means that we're going to have a normal with a location and scale associated with each mixture component. Here I'm using the Cholesky decomposition to define the covariance variance of the normal outcomes. And this just provides a more numerically efficient strategy for modeling that covariance structure. With this likelihood, our hyperparameters are going to be the means and sigma parameters, which I've selected here non-informative priors for. That just leaves our mixture hyperparameters, which don't have to change from our general recipe. We'll just be using the Dirichlet distribution to define those lambda mixture components. In the next slide, I'm showing how one could actually implement this model using the STAN language. And this is the language that I'll be using throughout today's examples. The main strategy here is in how we define the model block. This is where all of the sampling for our target posterior would occur. The first few lines specify the mixture component parameters, and then we have our hyperparameters of our likelihood, where I'm constructing the LKJ Cholesky covariance from a triangular correlation matrix, and then using a vector of scaling factors. The final step is our likelihood, which is on the log scale. For each K mixing component, an observation T, which in our serve case refers to a single match and server, we take the sum of the multivariate normal log likelihood, given the mixture parameters and the mixture probability associated with them. So each observation will have a value in the likelihood for each K component mixture. In this way, we can think of this term as a weighted average, where our weights are driven by the mixing component probabilities. The target that you see here is a special operator in STAN that collects all values and adds them to the full log posterior, which includes our hyperparameter and likelihood components. Okay, so one of the things when working with the finite mixture model is that we have to decide what value of K we're going to use. So we need this extra model selection layer. And one metric that's really useful for model selection in general, and one that we can apply in the case of choosing the mixture component K, is using the expected log predictive density associated with any model. The ELPD is a measurement of how well our model would be expected to do in terms of predictive performance when presented with new data. What's great with STAN models is that there's actually a really efficient way to estimate the ELPD using approximate leave one out cross-validation, which is implemented through the LU package. And what's really nice is that we don't have to actually split our data and run predictions for our test set explicitly. All we have to do is to specify an observation level log likelihood in our generated quantities block of the STAN model. And the LU package will actually give an approximate ELPD based on the likelihood. So the plot that you see here is an example of the results based on the served data example for components 1 through 6. And what we can see is that our ELPD improves gradually, but then begins to level off after component number 3. So this would be a clear indication that a choice of 3 for this problem would be an adequate one in terms of predictive performance. In the bivariate case, it's really nice to just use exploratory plots to visualize what exactly our components are doing. So in these plots that you see here, I've generated outcomes from each of the conditional normals, conditional on their component hyperparameters. So let's have a look at what each of these components suggest. In our first case, component 1, we see there's a very tight range of the distribution, with the mean for the first serve speed and the second serve speeds being pretty close to the empirical averages that we saw from the observed exploratory plots of our data. And we also see a very strong correlation between the first and second serve speeds. So from this, I think we could conclude that component 1 appears to represent the serves of an average ATP player's match performance. The third component on the far right is interesting in that we see there's a higher overall average on the first serve, where the average is close to 200 kph and about 20 kph higher than what we see for component 1. Also, the stretched ellipse tells us that there's a weaker relationship with the second serve speeds for this group. So this group seems to be characteristic of really big servers who can hit some of the fastest speeds that we see on tour, and where the power of the second serve is much more variable among this group. So that leaves this middle component, component 2, which is most distinguishing for how variable it is, where we see some of the slowest possible speeds as well as some of the fastest speeds. So this component really represents something of like outlier serve performance in either direction of the speed spectrum. As I was looking over the results for this model, I thought that there was one thing that maybe tennis fans attending this talk might be interested in, and that's how, in terms of our mixture distribution by player, the big 3 compare with some of the other players on tour, particularly a few of the next-gen players, some of the younger players that have been most successful so far in their careers. So the big 3 refers to Federer, Djokovic, and Nadal, who you see in the top row of this plot. And what I'm showing here is how often an observed match serve speed performance would fall into any one of the 3 mixtures. And what's interesting with them is that they are consistently falling in the component 1, our kind of average speed component mix. Whereas with our next-gen players, we see about 10 to 25% of the time, their serve performances are assigned to the third component. That would be the most consistent component with those match performances. So what could be going on? Again, remember that that third component refers to the very high first speed group of serves. Does that suggest then that maybe youth has some advantage for serve power? Well, I don't think it's youth, but what happens is that actually these next-gen players all happen to be about an inch or more taller than the big 3. So I think what we're seeing here is some effect of height and the kind of serves that are achievable based on the height of players. Okay, so now that we've worked through one example of a finite mixture model, let's have a look at one way that we can build on that basic structure. And the simple but powerful extension is to allow each unit of observation to have its own set of component weights, in contrast to the population mixing components that we saw with the first finite mixture approach. In this case, each observation gets its own weights, its own lambda vector, which I've denoted here with the index I. And when we do this, our likelihood can be thought of now as a sort of a weighted sum that's specific to that observation's own set of mixing probabilities. Because each observation is now allowed to have a different mixed membership of the component densities, it's known as a mixed membership model. And the LDA is actually one special but popular approach to mixed membership modeling. We could have considered using a mixed membership model for the served data, but I want to look at another example with a different type of observation outcome. So the question in the next application that I'm going to consider are a player's return patterns, where here the return refers to a player's shot in response to their opponent's serve. What's nice about this example is that it gives me a chance to point out one of the richest public data sets in tennis, and that's data compiled by the Match Charting Project, or MCP, created by Jeff Sackman. The MCP is a volunteer effort to code shot-level stats for historical tennis matches, and it's the closest thing tennis has to a retro sheet. Each charted match includes information about every shot that was hit, from the serve to the last shot of the rally. And over 8,000 matches have been coded and are available to view from the Tennis Abstract site. What can we use the MCP to say about serve return behavior? First, we can account for the context of the shot by considering the serve number, court side that the serve went to, as well as where the serve landed. For the characteristics of the return itself, the MCP includes categories for the depth of the return, as well as the type of return shot that was used, whether it was a forehand or backhand, and whether it was hit with topspin or slice. Altogether, these categories represent 144 different return situations. With these categories in place, I collected MCP matches from 2015 to the present for all players that are currently in the top 10 of the men's rankings. Each observation represents a player and single match with counts for the number of times a serve return was in each of the 144 types. So this is a multinomial type of outcome variable. In applying the mixed membership model to our return data, I did one additional extension, and that was to include win outcomes as well, which are denoted here as the WI outcome variables. These represent the number of times a return in a particular cell, cell D among our 144 categories, actually won the point for the returner. So this is a joint mixed membership model because we have both shot frequencies and win outcomes as conditional on our mixing components K, where we're going to allow each mixture component to have its own set of multinomial probabilities for shot frequency, as well as a set of binomial success probabilities for winning points for that given return type. Because this is a mixed membership model, every match is going to have its own set of mixture weights for the K component mixtures. So let's see what the implementation of this mixed membership model would look like. The primary point of interest is our likelihood contributions. Here we sum over the K components as in our earlier finite mixture model. But now we have both the multinomial contributions for the return type counts and the binomial contributions for the win outcomes for each return type. Also, the main difference from our previous example is that we have an index, an extra index now in our lambda mixture weights, where each observation is getting its own mixing probabilities. But otherwise, you'll see that our setup is very similar to what we had previously. Now, I'm going to apply the same strategy for selecting the mixtures in this model using the ELPD. And when I did that, I found that using a K of 4 provided the best performance in terms of predictive performance. This was the point at which that performance began to level off. Okay, so our outcome are more complex in this application with 144 dimensional outcome vector. So I'm only going to show a selected set of the results from this model. In the plot that you see here, I'm looking at the relative frequency of each return type for serves to the ad court. In each column, we're considering a different type of serve situation. And then in each row, we have return depth, and along the x-axis, the type of return shot that was used. So in any given column panel, we could take all of the rows associated with a given mixture and sum them across all of the rows in that column, and that will total 100. Okay, looking over the differences in the return patterns here, we'll find that there's one component that is a left-handed player component, where that player is going to play forehands for serves out wide and backhands for serves down the tee. It's the reverse for right-handers, and there are two components, components 4 and 2, that identify different types of right-handed return patterns. And looking over the general behavior between those two and how they differ, we would find that one of those components is a case of a player that plays with more backhand slice than the other. And the first component is an interesting one because it looks fairly uniform in terms of the shot frequencies, which might make us wonder exactly what purpose that component is serving. We can get some idea of that if we look at the corresponding success probabilities associated with these return types, which is shown in this image here. So again, these represent how likely we would expect the return player in that given shot situation to actually go on to win the point. And looking at that component 1, we see a number of cases where it has very different success rates for the same shot type compared with the other components. So I think what could be happening in our joint model is that that extra component is actually capturing some kind of additional dispersion in win success across the shot types. So that's an interesting result from the joint mixture model. Now, how do the current top 10 differ in their return patterns based on our model? Well, one obvious one is that we have Nadal, the only left-handed player in this group, as clearly distinct and the only one that's heavily weighed on the third component of the model. Among the right-handed players, the majority of them look very similar. There are two players, Roger Federer and Dominic Thiem, that differentiate themselves and show more of a use of component 4. And that is the component that has a heavier use of the backhand slice on the serve return. So that's an interesting thing that our model would suggest differentiates those players from the other top right-handers. Okay, so the last model that I want to discuss is a popular choice for sequential data. This would be data where we have a time index. So this could be, for example, looking at match outcomes from the start of the season to the end of the season, or something more granular like the sequence of shots within a point. The hidden Markov model gives us a strategy for estimating latent quantities that influence this sequential process. The main idea with an HMM is that we consider the unit of analysis at any time t as being in some set of discrete latent states, here denoted as S. That latent state determines the generative model that defines our observed outcome at that given time. In this setup, we need an additional layer to the model to define the transition process from one latent state to the next. In the HMM, each move to a new latent state depends only on the current latent state and its set of transition probabilities. In other words, the latent state transitions are defined by a first order Markov chain. In terms of our Bayesian recipe, let's see how our setup would differ in the case of an HMM. So the main thing you should notice is that now our observations and our parameters are going to have an index t to indicate the time sequence of our outcomes. At each time point, we have the same conditional distribution, conditional on the mixture component k, which is now representing the hidden state at time t. After initialization, the hidden states are generated by the transition matrix A, where each row is a set of transition probabilities that correspond to a simplex. And if we think about it, at any given time point, that single row of transition probabilities is just like our lambdas from the previous finite mixture model examples. So this tells us that we can think of HMMs really as time-dependent mixture models, where at any time t, we're really back to the finite mixture model that we started with. And I think this is a really great connection and shows how large a class mixture models really represents. Okay, so let's think of an example where we might use an HMM in sport. One application I've been thinking a lot about over the past year is the use of latent models for understanding rest management and injury. Studying injury is really hard in sport just because data for injury is nearly always incomplete or of questionable quality, and that's certainly the case for tennis. But what we do know with great accuracy is when players are competing and when they aren't. The plots that you see here are actually sequences of the competition schedules for the current top 30 best male players in tennis, where each green square corresponds to a competition week where that player was in competition in 2019. The question I want to put to you is whether we can use this kind of data to understand something about the frequency and duration of injuries in elite tennis. So if we look at most of these competition schedules, we see that players are playing regularly throughout the 46 weeks of the regular season. And rarely do we see instances where a player is out of competition for 3 consecutive weeks or more. Several of the sequences at the top, however, deviate from that pattern. And if we do some digging on the web, we'd actually find that those players did have injury-related breaks in 2019. Okay, so this suggests that we can make use of this information to maybe understand something about the frequency and durations of injury. A simple starting point is to think of players being in just 2 latent states at any given time during the season. Either the player is healthy or injured. So these would be our latent states. Now, there is some art to specifying latent state models, but one guiding principle is that any latent state should have a distinguishable emission distribution, or the conditional distribution for our observations. If every latent state gave us very similar observed sequences, there wouldn't be much point to distinguishing among them, would there? Further, having these distinct characteristics for the emission distribution is going to really be essential in order for us to have any chance to identify the different latent states. So let's see how exactly this might work in the competition scheduling problem. Now that we have our 2 latent states, what would the emissions look like in each of them, and how would they differ between each other? In our case, emissions are really just whether or not a player is competing. So we have just a 2-state outcome, which we can describe with the Bernoulli probability. Those are the theta parameters that you see here. The question is whether we can put some expectations around that probability for each latent state. Based on the schedules that we saw before, I think a reasonable assumption is to expect players to be competing more than they're resting when they are healthy. These players need to make a living after all, right? So we could represent that expectation by constraining our theta 0 parameter to be greater than 50%. When injured, on the other hand, a sensible player should be resting more than competing, implying a theta 1 of less than 50%. So in our model notation, we have 2 latent states and a Bernoulli outcome for each competition week. We need just 2 success parameters to define our likelihood, one for the probability of competing when healthy, denoted here as state 1, and one when injured as state 2. One of the great things about SCAN is that we really have a lot of flexibility in imposing constraints on variables. One that I like when we have bounded variables is to use a bounded logit, and that's what I've suggested here. So to differentiate our 2 states, I'm going to put a constraint on the theta 1 parameter to be between 0.5 and 0.1. I can do that by first drawing the standard normal, the tilde theta 1, and then using this bounded inverse logit transformation. For theta 2, it's the same process, but I'll use a different bound so that it will be forced to be between 0 and 0.5. And this is going to be our main strategy for identifying those 2 latent states. Finally, we use a Dirichlet prior for each row of our transition matrix, just as we did with the simple lambda mixing probabilities in our finite mixture examples. With the release of STAN 2.24.1, we have a number of high-level functions to help us fitting HMMs, which is really great. The main function needed for the model statement is HMM marginal, which calculates the marginalized log likelihood contributions of our frequency, marginalizing over the unknown latent state sequence. To use this function, all we need to do is to calculate the conditional log likelihood of our observation at each time t and for each latent state. So if we have t time points and k total latent states, we would have a k by t matrix of log scale conditional probabilities. We would then supply our transition matrix, A, and an initial set of initial state probabilities. And this is all that we would need in order to fit the target posterior for our HMM. In addition to helping calculate the log posterior, STAN also gives us a convenient function for sampling from the latent states. And this takes exactly the same inputs, the main difference being that this sampling would go into our generated quantities block rather than the modeling block because it's not actually involved with any of the model fitting. And it would return a sequence of integer values corresponding to the latent states, posterior most probable latent states for that point in the sequence. Okay, so let's see how our HMM would actually look in the STAN model. First, we start with the model block. At the top, we define the n matrices, each having S latent states and T observations. Each n here corresponds to a single player season. We then calculate the log likelihood for each state, which is simply the Bernoulli log likelihood for the competition scheduling problem, each theta being specific to the S latent state. Finally, we set the priors for the latent transition matrix and the initial states. We then loop through our observations, adding the value of the HMM marginal to the target posterior in each case. For sampling from the latent states of our model posterior, the curve is very much the same, but again, as mentioned before, it's now within our generated quantities block. And this will be a way that we can easily inspect the latent state distribution resulting from our fitted model. I ran the model that you saw here for seasons 2016 through 2019 for the top 30 players that we saw in our earlier plots. Because of our emission probability constraints, the labeling of the latent states is very easy. In this case, we find that the healthy state is very sticky, with players who are healthy in 1 week expected to remain healthy with 98% probability. Injury is also sticky, however, and once a player becomes injured, it's expected that the injury will persist for more than a single week. We can actually carry out the transition matrix steps to their limit to determine the steady state frequencies of the latent states. And that shown on the right would suggest that in any given competition week, we would anticipate that about 10% of players would be injured. And how likely are players to compete when they're healthy? The posterior distribution of our theta parameter suggests that it's between 60 and 70%, which is consistent with our observed schedules. When injured, as expected, this probability is close to 0, but not 0. But it is still a very unlikely event, with the density being all to the left of 10%. So one of the potential applications of our competition scheduling model is to look at the period of probable injury or other causes of unexpected absences based on historical competition schedules. The plot you see here is the latent state sequence for our fitted model for Nadal for seasons 2015 through 2019. All the areas of purple are areas where we would expect Nadal's competition schedule to be more consistent with an injured state than a healthy state. And we see that there are periods in 2016 and 2018 with long time periods that would suggest he had been injured. For a player like Nadal, whose every move tennis media and millions of fans are following closely, this would come as no surprise. We could easily find information that would tell us that Nadal had in fact been injured during those periods. But a programmatic way to identify periods of possible injury could be really useful for the hundreds of other professional tennis players who don't get the kind of week-to-week attention that the big three do. Here, for example, is the schedules and the latent state sequences for Matteo Berrettini, one of the rising stars of the next generation in the sport. Here we see that our HMM results would suggest nearly all of the 2016 season was spent in an injured state. Yet for Berrettini, if I look at his English wiki page or coverage in the English media, I wouldn't really find any information to substantiate that period. So even though this is a very popular player, we still wouldn't necessarily be able to confirm all periods of injury from what information is publicly available. And this would be one basis for using an HMM like we've described in this example. Okay, to wrap things up, I do hope that this survey of models and example applications have shown that mixture models are a powerful class of models with many possible uses in sport. The finite mixture, mixed membership, and HMM will cover a lot of interesting problems, and I hope I've shown how flexible languages like STAN can allow us to build and extend on these frameworks. I promoted STAN a lot in this talk, but I do want to emphasize that we can use other strategies for inference with mixture models. And there are two particular cases where an alternative to STAN would be necessary. The first is when there is a need to put a prior on the latent state itself and not just the mixture probabilities for the states, essentially when you don't want to marginalize out the latent states. STAN does not support sampling of discrete parameters, so you would need another option in this case. The other thing, and one that might come up most for those of us working with sports data, is scale. For really big problems, where our data sets are massive, STAN sampler may be too slow for practical usefulness. Now, STAN does support parallelization, as well as provides other methods of inference, such as stochastic optimization or variational inference, that can help speed things up. But for really big problems, it might be necessary to consider more highly efficient languages like TensorFlow probability, for example. Still, I think the set of tools I've shown in this talk are powerful ones that I hope you find a use for in some of your own sports research. And if you have any interest in more details about what I presented today, please feel free to drop me an email at my Zelus address. I'm happy to talk about mixture models as well as tennis stats at any time. So thank you for your attention.